Everybody, so today we have here the fourth what is seminar of Josué Tonelli-Cueto. The first one was in 2006 about origami constraint to a number, which I unfortunately couldn't attend. Then there was about the length of the potato. What was the third one?
The probabilistic complexity class.
Yeah, and now this is something about semi-algebraic sets in context. So we are happy to listen to it.
So let's start with the basic definition of a semi-algebraic set. So semi-algebraic sets are used sets that you can describe with real polynomials, inequalities, and set theoretical operations. So essentially it's one way of doing it is you start with some real polynomials, f1, f1, and then you have a system of this form. Here you will get, let's say, x equal to 0, then d1x 0 equal to 0, dsx equal to 0. Okay, so this is a semi-algebraic set. So it's one of these polynomials is real, and we are using to rest it in real variables because otherwise greater or equal to 0 doesn't make any sense. And this in the complex setting. Okay, so once we have this is usually, this is S, usually this is denoted by B, because these are what are called B of passive semi-algebraic set. And then from here one passes to what is a general semi-algebraic set, which is just a finite union of basic guys where this is passive. Essentially, basic semi-algebraic sets, you can just describe it by a system of equalities and inequalities. And then a general semi-algebraic set, you have to put unions inside. So this is the same as putting or statements. Or it satisfies one system, or it satisfies the other system. And you can even do more complicated stuff. But so this is pretty easy to get. And here is nothing. Go. So let's go with the first example. So, sample 1. So let's go with the number of roots of univariate polynomial. So imagine that we are given some univariate polynomial and one variable p belonging r t. Here we put less or equal to t. Essentially here I mean less or equal, let's put it in the meaning that p has degree. So this will be division. I will just mean that degree of p is d. Okay, so once I have this this class of set, a question that I can ask in the real setting that makes sense, but not in the so in complex setting, this will have d complex roots. That's all, nothing to do. In real algebra geometry, you have to start worrying about the number of roots that it has. Because in a way, in real algebra geometry, you don't care about the complex roots. You care actually about how many real roots the polynomial actually has. So essentially, you are interested in seeing how you can describe, for example, the set of P has, let's put member, put here n real roots. Okay. So in the complex, in the case that P is a polynomial of degree 2, and that is described in the form of at squared plus pp plus c. You can use define what is called the discriminant, this famous guy that appears when you solve the equation, and then you have essentially that the p such that p has 0 roots is essentially described by the set p such that lambda p, this is less than 0, then you get the same, but now with one root, then you get the discriminant has to be equal to 0, and then this, then you get discriminant has to be positive.
So we're meant to say for that set that's not all polynomials, but degree 2 polynomials.
Yeah. Yeah, in this case we are focusing on degree 2.
So you fix the
Yeah. Here I fix the degree. I mean, you can also do for the lower ones, but I mean, it makes things easier. Maybe this is not the best notation, maybe this would be better, but that's not the point. So, one thing that is easy to do is, this is easily generalizable to the case of degree 3. There is also discriminant in that setting, and you can play the same role and seeing how many real roots you have. More or less, you will get the generic cases are easy. When the discriminant is 0, you have to have a little bit more of care, just to see if it is a double complex root or if it is a double real root. But you can do the same thing with an extra guy. And in general, when you do this, one can prove that this guy is a semi-algebraic set. This is not immediately trivial. And so this is like a particular case of I consider a real polynomial, I consider some property of the zero set of the real polynomial, and then I'm wondering about what is the properties of that what are the properties that I have to check on the coefficients so that certain property of the zero set holds. Usually this will be described by semi-algebraic sets. So this will be the first kind of example. Then we go below to a new class of examples, which is essentially projections. So in the projection setting, I have here, let's consider a very simple set, essentially x squared plus y squared plus z squared equal to 1. This is essentially a sphere, everybody knows this. Then one gets here pi, which is just a guy that will set x, y, z to x, y. So this is coordinate projection in the first two coordinates. And then when one looks at PV, then suddenly we get this inequality. So essentially we get a semi-algebraic set. Then one can also show in a similar fashion, repeating this example with a little bit more of care. You can check that if you start with this algebraic set, so here we put the ix to the square, then here we put this is summatory over I, this is over j. Here I put this tj minus gj x, here I put the square. Here I put the square equal to 0. Now the projection t will take the tuples of the variables. So this is a tuple of variables x, this is a tuple of variables t, and I just forget about what was in the t's. Then one can check that this guy here, PV, is just a basic semi-algebraic set described by this is equal to 0. These guys are positive. How to see this? Okay, if this is 0, this is sum of the squares over the reals, then it's one of the summands have to be 0. The only way in which you will get this here is if this guy is 0. Here you will get this if there is some real number whose square equals this polynomial. This can only happen when this guy is non-negative. And then essentially this is why you get this. So essentially when you so this is one way, but then in general one can even solve one more general theorem. Let's write it here. This is probably one of the most important theorems in semi-algebraic geometry, because essentially this theorem is saying that for all semi-algebraic sets, yes, and all Let's put it here. So for all semi-algebraic set S and all, let's put here polynomial maps just to let it simple. So this will guide R to the N, and then I got a polynomial map that goes from R to the N to R to the M. Then we got the Fs is semi-algebraic. And even more, there is a thing. The description can be obtained algorithm. Essentially, if I give you a semi-algebraic set, in particular one of these real algebraic sets, I give you some polynomials, then I give you some polynomial map, and then I ask the question, how does the image of this guy looks like? Then you have an algorithm that essentially will produce you the description of the semi-algebraic set. So it's not just that you obtain a semi-algebraic set, but there is an algorithm that gives you the description. So you have a way of doing this.
Just saying the description, I would just think it's usually a description, but if there's some kind of uniqueness for a description of
This is a description.
What do you mean by description?
Like I give you some sort of systems or a formula like with given by real polynomials and inequalities with unions and intersections, and a polynomial set belongs to my semi-algebraic set if and only it satisfies, follows these inequalities and these descriptions. So sort of, so essentially, or one of the polynomial vanishes, or the other ones are positive, bigger or equal than 0. So you have like one block of conditions, and then you add all this other block of polynomial conditions holds. And then you can put Boolean combinations of this. So statements like or something.
That's never unique, though, right? That's not unique.
No, but you can always, you can always, there is a description that you can do unique, but this is not the best one always. This is a description. Can be obtained. Okay, so we have this theorem Tarski Seidenberg. One important corollary of this theorem. So one of them is if you want to study real algebraic geometry, you will be forced to consider semi-algebraic sets, because many objects that you are interested in real algebraic geometry, for example, polynomials with a number of real roots, can be expressed as a projection by a polynomial map of an algebraic set. And then you will get, okay, the object that I obtain will be still an algebraic set. And there are a lot of other things. But then one important corollary of this, and one of them is, okay, I will erase this part. A part to what is called quantifier elimination. So this will probably be an example in logic. So one thing that if you have a property P, so P is a property on x and y, or it holds or it doesn't hold, then you can consider this set x comma y belonging x times y such that P of xy, so essentially the property holds. Then if you do the projection, so if you use the projection onto x, you will obtain the set of x belonging to x, such that exists a y, such that belongs y, such that pxy holds. So whenever you do a coordinate projection, it's like if you are putting an existential quantifier in the property that you are doing. The similar trick by taking complementation, then projecting, and then taking the complement again gives you the for all. So then in general you have like guys of this form. For x2, here you do xn, and then here you say that x1 xn comma y belongs to s, and here we are assuming that the qi is right here. Qi belongs to for all existent, and then is semi-algebraic. Okay. So you have a set of this form. So you have a big semi-algebraic set, and then you have a set of quantifiers. So for all x or whatever. Then this theorem, in a way, what says to you is that this guy here, the whole array, is that this guy is semi-algebraic. So essentially, I can eliminate the quantifiers. And because I get that this I can do in an algorithmic way, the second corollary, that probably this is one of the most impressive ones, is that whatever this means, first order theory over R plus dot with order is decidable and complete. So essentially, whenever I give you a step